Next, we need to think about velocity and the diameter of a single vessel. So think about a garden hose. If we put some volume of water in at this end, say we put 1 liter in per second, fluids are relatively incompressible. So if we put 1 liter in per second, that means 1 liter per second has to come out the other end. 1 liter per second in, 1 liter per second out. What if there's a constriction in part of this tube? If we're still putting in 1 liter per second, we must still be having 1 liter per second leave on the other side. Let's zoom in here for a second and say that here's our liter. Each of these is 1/4 of a liter, moving this amount in each second. Over time, this water is here, the same 4/4 of a liter, 250 mils each, and again, they move that far in a second. What happens when they get to the constriction? When they get to the constriction, they cannot all go through side by side. The only way to get through is to line up. Instead of moving this distance in 1 second, now they have to move 4 times the distance. As these come out, they now can fit, and so now they go more slowly, this distance in 1 second. So if they're moving this distance in 1 second here, they have to be moving 4 times faster when they go through the narrower constriction. So if we apply that to an animal pumping blood out of the heart through arteries, it'll increase speed with lower cross-sectional area. But it will also increase resistance with lower cross-sectional area. A cost of higher speed means more force, stronger contractions. Blood moves through the circulatory system in response to pressure generated by the ventricles. Pressure is the force of random molecular motion pushing molecules against each other and bouncing them off the walls of a vessel. But a lot of the energy of fluid moving through a tube is momentum. A portion of the random molecular motion being directed, in which there's a net movement in one direction. And that momentum tends to keep fluid moving forward. Fluids actually move from areas of greatest total energy to areas of lower total energy. That doesn't matter when there is no particular directed movement, but one of the consequences is that it matters that vessels actually branch off from each other at slight angles, because a branch like this will bring a lot even distribution of blood between the two branches than a branch like this, in which momentum will put a greater tendency to move fluid in this direction than this direction, even if the vessel diameters are the same. In physiology, there's another important element of this same point, which is at an area where there's a sudden ballooning of the tissue. So imagine an aneurysm where the vessel wall has weakened and thinned, and as a result it's bulging out because it's not able to withstand the pressure as well. That's an aneurysm. Physics that I just talked about has an effect on the tendency of aneurysms to get worse. Fluid entering the area of an aneurysm has laminar flow in the center of the vessel, slower as it gets closer to the boundaries, and of course turbulent flow along the boundary layer. As it enters, because of the opening out, fluid slows and it has to spread to fill this space. And so vortex currents, like so. Fluid going through an aneurysm has some of its energy of momentum, or inertia, converted to random molecular motion because of this turbulent flow. And the turbulent flow also puts additional pressure. Some fluid hits against the vessel walls. In an aneurysm, that random molecular motion is increased heat and increased pressure. So in an area that is already weakened, it also has the most pressure, making it even more likely to burst. Now let's think about the circulatory system as a whole. In one sense, it's equivalent to a long tube, a garden hose, but it starts as a single opening, the aorta, and then immediately starts to branch off other arteries. Each element contributes resistance. You can think about each individual location contributing its own share to the resistance. We can add all of those by looking at what's called the total cross-sectional area. The total cross-sectional area would be all of these different parts. And we can add all of them up from every single location among the arteries to get the total cross-sectional area of the arteries. And we can do the same for capillaries. Each capillary is tiny, but you have miles of them. And so the total cross-sectional area of the capillaries, when you add them all up, is much higher than the total cross-sectional area of the arteries. The veins are somewhere in between. Again, we can total up all of the veins, from venules to large veins, and again we get a total cross-sectional area. If we plot that to get a sense of what is the resistance in arteries, capillaries, and veins, on the y-axis we have total cross-sectional area. What we'd find is that arteries are relatively low in cross-sectional area. As we go to arterioles, they start to go up. By the time we get to capillaries, it's high, and then for veins, we go back down to an intermediate level. Because the total cross-sectional area in arteries is narrow, you can think of them as a constricted area in a garden hose. And so blood moving through the arteries is fast. It's like the narrow part of a river or a stream. The total cross-sectional area of the capillaries is very high. And so blood moving through the capillaries is slow. That creates high time, a large amount of time for exchange. In the veins, the rate of movement is intermediate, and that's not a problem in veins. They're not delivering essential materials fast to any tissues. They're simply taking wastes and carbon dioxide to excrete. That intermediate rate of transfer is fine. The skeletal muscle pump and the relatively low pressures of blood coming out of the capillaries is sufficient to move blood from the veins back to the heart. Among vertebrates, selection appears to have favored fast movement through the arteries, slow movement through the capillaries, and slow movement through the veins. Pressure also changes with distance from the heart. Pressure in millimeters of mercury from 0 to about 150. And we'll look at arteries, arterioles, capillaries, venules, and veins. Depending on the extent to which you're exercising, pressure in the arteries may be as low as 100 or so and could be above 150. Let's start with somewhere around 120 into your arm. Pressure is going to decrease with distance because the energy of pressure entering is continually being lost. Part is simply collisions of molecules from the blood with the walls of the vessel, which transmits some energy to molecules on the outside of the blood vessel. Energy is being lost as energy of vibration and of heat. That decreases pressure with distance. In addition, that pressure is traveling as a pulse in which the elastin molecules in the artery walls are being stretched, and then as that pulse passes, those elastin molecules go back to their original shape. That elastic recoil recovers some of the pressure loss, but some of that energy is lost as heat. It's lost as heat partly from displacing the molecules and the tissue on the outside of the blood vessel, and partly it's lost because the elastins are not 100% efficient. You're losing some energy as heat. So the pressure may start at somewhere around 120. It declines through arterioles. By the time it gets to capillaries, it's down in the range of 30 or lower. Declines further through the capillaries and is down near 5 to 10, sometimes even lower than that by the time it gets to the venules and the veins. That pressure is enough to move blood back, but the skeletal muscle pump is adjusting that. Muscle movements and pressure will raise that up and down. So, and in particular, when you're exercising, skeletal muscles are working hard, and that can produce significant raises in pressure in the venules and veins, returning blood to the heart.